Hello everybody, this will be our last lecture on special relativity. So far, what we have discussed is mostly the kinematics of a particle, how its position and time measurements and measurements related to position time changes in between different reference frames. What is the relativistic effect on those? That means that what is the effect when things are moving near to the speed of light, at the speed near to the speed of light. Today we will talk about dynamics of a free particle. So what do I mean by a free particle? Free particle means it is not acted by any force or potential. No force and constant potential, because you know that if the potential is constant, then there is no force. Now, before we go to the relativistic case, let us first discuss the non-relativistic case, which we have already done. And as in this course, we have been dealing with Lagrangian and Hamiltonian dynamics. So let me do this in the light of Lagrangian and Hamiltonian dynamics. So we start by writing down the Lagrangian. Of the particle. And say the Lagrangian, so it's a particle moving in all three directions. So I can have x, y, z, and can also be a function of x dot, y dot, z dot. It can be a function of time as well, but you know that for the free particle it is not the case, so I don't put the time over here explicitly. And for the free particle, this is just the kinetic energy, which is half m x dot square plus y dot square plus z dot square. Okay. What do I do? Just after this, I find out what are the momenta. So what is the momenta? So these are canonical momenta. And this is the momenta that is the only momenta that we talk about. We have the definition of our momentum in terms of the canonical momenta. So they are px, py, and pz. This is del L, del x dot, and you know what it is. If I do del L, del x dot here, I get 2x dot, cancels the half, I get mx dot. Similarly, this is del L, del y dot, my dot. I can go and find the Lagrange equation also, but let us look at what will be the Hamiltonian for this free particle. So Hamiltonian, remember H is P I Qi dot. So let me write, okay, so let's write Qi dot minus L. In this particular case, it will be Px x dot plus Py y dot plus Pz z dot minus L. And I should write things in terms of momenta, right? So Hamiltonian, if you remember, is a now function of x, y, z and px py and pz. So In terms of this, the x dot I change to in terms of p, so I get px by m. So this will be px square plus py square plus pz square by m over here minus L, and L is these quantities, but x dot square I can write x dot square as px square by m square plus dot 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 for y and z. So if I put those, this will be just half of the first term. And remember the Hamiltonian free particle, this is a constant, and the constant is what we call the energy. So the left hand side is nothing but the energy. The right hand side, what I get, px square plus py square plus pz square is just p square, and this half makes it p square by 2m. P square is the square of the amplitude of the momentum. So that gives me a relation between the energy and the momentum. So this is how I do Lagrangian and Hamiltonian mechanics. I could have written down the Euler-Lagrange equation and the Hamilton's equations. I don't want to do that for a certain reason, because there are complications, and we will not go into those complications in this lecture. Okay. So one thing, let me tell you, is that so let us ask this question: how do we define a particle? In classical mechanics, a particle in classical mechanics, it is a point-like object. So it's a point-like object. Point, you know that it doesn't have any dimension. It's an abstraction. Don't think that such objects does exist, but this abstraction gives us good result, good predictive power. It has certain properties. So what can be its properties? One property we always use in mechanics is mass. So if I tell you this particle has this mass, it's a mass which is fixed to that particle. It defines the particle. There is no way I can say that in a different reference frame I will have a different mass, because if it's a different mass, it's a different particle. So the particle, I'm talking about the same particle as seen by observers from different reference frame. So the mass of the particle cannot be different in different reference frame. This is the point of view that we are going to take in this particular lecture. And I'll give you a lecture note, and there is another point of view, about another point of view, written in the lecture note, which I am not going to discuss during the lecture, because otherwise it will confuse you. Okay, but the other point of view also exists, and you may look at the lecture note to see what is the other point of view. But for us here, the mass is something that defines the particle. It doesn't care, it doesn't mean which reference system you are looking at the particle. The mass is always same, it defines the particle. You change the mass, it's a different particle. I cannot say that I am looking at things happening with the particle called Bob in one reference frame and the particle called Billy in the other reference frame, right? Uh, Different reference frame, different observers are always looking at the same event. Other things can be like charge, etc. So just let me write mass and charge here. Mass is the thing that we need mostly, because see, charge is related to a potential, electrostatic potential if you wish, and so you don't have any potential, you are dealing with free particles here. So let's come Lagrangian now for the relativistic. So what do I mean by a relativistic free particle? If free particle, so it's not influenced by any force or any potential, or at least a constant potential at max. But it's relativistic. It essentially means that it has a velocity. It's a free particle. It has constant velocity. Its component x dot, y dot, z dot. None of these are anywhere. These are near to the speed of light. In the first case, non-relativistic case, this essentially means that x dot, y dot, z dot, remember these are constant, are much, much less than c. Now that is not the case anymore. Now for this, one can actually derive the Lagrangian. I will not say derive, but one can guess what the Lagrangian is. If I ask you, how do you get what is the Lagrangian for a free particle in non-relativistic case? Somebody told you it is t. There is a potential t minus v. You do not know how to get to that. It's an assumption, or it's a first principle if you wish. Here also, I have to write down the Lagrangian. There is a way of arguing about it, but I will not do that for you because it goes beyond the scope of this course again. So Lagrangian is a function of these quantities, and the free particle Lagrangian for a relativistic free particle is given like this. V is the speed of the particle. So V square is essentially x dot square plus y dot square plus z dot square. Okay. So this is somebody is already telling you, somebody is giving you this Lagrangian. One question you can ask is that what is the non-relativistic limit? What is the non-relativistic limit of this Lagrangian? What do I mean by that? I mean, say, okay, since we have seen that the Galilean transformations are the Lorentz transformations when the velocity speed of the light is rather small. Sorry, speed of the particle is rather small, or the speed between the reference frames are rather small compared to the speed of light. So when I say non-relativistic limit, it essentially means that when v is much, much less than c here. So then the Lagrangian should not be very far from our old Lagrangian of half mv square, right? So let us take the non-relativistic limit. So what happens then? So L is minus mc square root over of 1 minus v square by c square. And we have discussed Taylor series approximation before, so we'll do the same thing here. So v by c tends to 0. That is the limit. In that limit, I can write this 1 minus v square by c square as 1 minus half v square by c square. That's the Taylor expansion. Root over of 1 minus v square by c square is to the power half, and that half comes here essentially. And what is this? So this first term is minus mc square. So let me write this n. Just to remind you, this is the non-relativistic limit. So let's call it LNR. Plus c square cancels out. So this is half mv square. You see, it's a good old Lagrangian in the non-relativistic Lagrangian, half mv square. But there is an extra term over here, which is minus mc square. But you see, m is a constant. M is the mass of the particle, which is said is the property of the particle. C is the most stringent constant that we have heard so far. So this is a constant, and we know that adding a constant to the Lagrangian doesn't change anything about the dynamics. So this Lagrangian, which I have written here, the relativistic Lagrangian, really goes to the non-relativistic Lagrangian of half and v square if I take v much less than c in that limit. All right, so let's see what we can do with this Lagrangian. So first thing that we should do is to find out the conjugate momenta in the relativistic case. So I have px del L by del x dot. What will this be? Okay, so the calculation is a little more non-trivial now, but let us do it. It's not very difficult. So I get mc square outside. So this is my L. And remember that v square has x dot in it. So I have to the square root over v square there. So once I do the derivative, I will get a half because of the square root. And the square root of 1 minus v square by c square, what will give is half, and then to the power half minus 1 is to the power minus half. So this will come in the denominator. You can just do the derivative. And then I have to take a derivative of 1 minus v square by c square. V square obviously is, 1 obviously derivative is 0. So once I take the derivative of minus v square by c square, I get a minus 1 by c square. And partial derivative of v square with respect to x dot is just 2x dot. So here I can write 2x dot. So what do I get as px? Let's see. C square cancels out. Half cancels out with 2. The minuses cancels out. So m remains. X dot remains. And then remains 1 minus v square by c square. Or I can write this as m. X dot is vx dx by dt. And 1 minus v square by c square is nothing but gamma. So you realize that px is almost as the previous canonical momentum, which is mvx, but there is a correction factor of gamma now. And if you calculate the other ones, you will also see they're similar. In fact, I can write the vector momentum as m, the vector velocity, times gamma. Vector velocity has 3 components, vx, vy, vz. Vector momentum has 3 components, px, py, pz. Okay, so these are again just like the previous case, but there is a correction by gamma. Remember, gamma is greater than 1. So if you are moving with very fast speed, then your momentums will increase much larger compared to your non-relativistic momentum. Also, you realize that the momentum does not increase linearly with its velocity, because I have v over here, I also have v in the denominator in terms of gamma. So there is a v square by c square in the gamma. So the momentum doesn't increase linearly with velocity. It increases non-linearly. Initially, when v is very small, v square by c square tends to 0, gamma tends to 1. It is almost linear, but later it becomes non-linear. Okay, so here let's write that momentum does not increase linearly with velocity. So that's an observation that we have made. What next? What next is the Hamiltonian, which will give us the energy. Okay. So how do I write down the Hamiltonian? The Hamiltonian is P Q dot, which is V. I can write this way, minus L. What is P? P is M V gamma. So I write M gamma V dot V, and L in terms of V is written here. So minus mc square root over 1 minus v square by c square. So let's write that down. Minus mc square. Let me write so that root over 1 minus v square by c square in the numerator is 1 by gamma essentially. Okay, so let's calculate h here. It will take a little bit of exercise to do that. So let's take m times gamma common as outside. So the first term is v square. M I have taken common and gamma I have taken common. So c square remains here and 1 gamma is taken outside, but this is by gamma. So this is c square by gamma square. Remember that Hamiltonian of a free particle gives the energy, right? So this, the left hand side is essentially energy of the relativistic particle moving with a velocity v. So right hand side is m gamma. The first term is v square. Here I have c square. And what is 1 by gamma square? Remember 1 by gamma is root over 1 minus v square by c square. So this is just 1 minus v square by c square. This is what I have used here. So this E, then m gamma, first term is v square, then I get c square, then plus c square cancels out, I get v square again. I'm sorry, see here it should be plus because the Lagrangian is minus mc square, right? So this should be plus, this should be plus, this should be plus, and now my desired minus has appeared here. So you get E equals m c square times gamma. It's the energy of the particle moving with a velocity v. Particle has a mass m, and that velocity v is hiding inside that factor gamma. Okay, this is just like the kinetic energy, if you wish, because what we call kinetic energy is the energy a particle have if it is not imparted by any potential or force. Energy of a relativistic free particle. if the particle is at rest, so you can ask the question, what is the energy of a relativistic free particle at rest? So for a non-relativistic free particle, that is zero, right? So in this case, I can calculate that just putting gamma equals to 1. What will I get? So let's call this E0 because the particle is at rest. It is not 0, it's mc squared. You see, that's how to write down the most celebrated, most well known, most famous equation of the world. E is mc squared. That is essentially is telling you particle at rest not influenced by any potential still has an energy given by its mass. This is the meaning of the most famous equation. Okay, so you're almost done, but you see there is one thing left. We have written down the energy in terms of gamma, but gamma is written in terms of the velocities, not the potential. And the potential and velocity is related in a little complicated way for relativity, right? So this I should also put in a box because this is one of the important relation. If I want to really write down the Hamiltonian, I should be able to write it down in terms of the potential. So let us try to do that. Okay. Instead of writing H, I am writing E. Okay. And let us calculate what is E square minus P square C square. So what is this? E is mc square gamma. So m square, E square I have here. So m square c to the 4 gamma square. P is mv gamma, and when I say p square, everything will be squared. So m square v square gamma square and c square. Okay, so this is p square times c square as in the left hand side. So let us take m square c to the 4 and then gamma square outside. So first term becomes 1. In the second term, m square is gone, gamma square is also gone. I have a v square in the numerator, and I have c square here, but I have taken c to the 4 outside. Second v square by c square. But v square by 1 minus v square by c square, 1 minus v square by c square is just 1 by gamma square. You can see it here. So this is gamma square by gamma square. So what I get is E square minus p square c square as m square c to the 4. See, m and c are both constants. So this is again gives me the relation between the energy and the momentum. Just like I have, so this is relativistic case. In the non-relativistic case, it's a quadratic relation, which is this. And both are obviously for free particles. That's all about all the relations. So this is non-relativistic. So what have we done so far? What have we done today? So we have written down the Lagrangian for a relativistic free particle. So this is the Lagrangian. And then we calculated the canonical momentum. The canonical momenta got modified by the factor gamma. So if there is a non-relativistic particle, gamma is almost 1. It is the old canonical momentum relation. But otherwise, we realize that the momentum does not increase linearly with velocity. It increases in a complicated way because gamma also has V in it. Then we calculated the energy. The energy comes out to be mc squared times gamma. So energy of a particle having a velocity v is mc squared times gamma because gamma has the information of the velocity. So gamma is, remember, 1 by root over 1 minus v squared by c squared. And we realized one interesting thing here. If the particle is at rest, then v is 0, gamma is 1. The free particle not influenced by any force, any potential, it's at rest, still it has some energy, which is equals to mass times c square. And that is the most famous equation of all time. Everybody knows E equals to mc square, even if they do not know what is E, what is m, what is c, what do you mean by square, and even what is the equals to sign in between. But still, now you know exactly what it means. And then we also got to the fact that how the energy and momentum are related in a relativistic case. Okay. We'll discuss one more thing. This does not come out of this discussion, but it's another result which one can arrive for the relativistic case. And it kind of can be shown from here, but does not come from here. And where it comes from is a little bit more complicated, so we'll not talk about. So we'll talk about a particle. If there is a particle, we said mass is an attribute of the particle. It defines the particle. So I'm defining a particle now with mass 0. So what if there is a particle with mass 0? So you see, if the mass is 0, I get E is equals P by C. It does not come from there, but believe me that for a particle with mass 0, E is equals P by C. But P, which is now is the magnitude of the momentum, can be calculated from the energy of the particle this way. Okay. So this essentially tells you, it's interesting, right? Always we have said that momentum is something as mass times velocity. We have seen that is not true. But now we realize there can be momentum of a massless particle. Later, people realized that the particle of light, what we call photon, is such a particle. And again, it is true, and it has real consequences that the photon has mass. And let me tell you a little bit, because we have a little bit of time left, let me tell you a little bit about the consequence of photon having mass. Photon is light, right? So it's a particle of light, if you wish. So we have these satellites in the orbit of the Earth, right? So I'm just drawing a cylinder, which you imagine it's a satellite. It's going around the Earth, and you see they're not drawn in proportion. This is Earth. The satellites has neat power. Because of that, they have these solar panels, and usually there are one in either side. Let me draw it a little bit. So I remove this. So it has solar panels. The sun is somewhere here. I still draw the sun a little bigger than the earth, but none of them is, obviously the satellite is not bigger than either sun or the earth. So the sun is giving light to the solar panels, and that is what is giving power to all the electronics in the satellite. It's being able to communicate with Earth. But you see, this light does not only bring the energy, with the energy, it also brings a momentum. So that momentum is being pushed by the solar panels. The solar panels are pushed by the momenta, and the satellite will start moving in this way. So it will go off course. You know, the satellites it's supposed to stay in an orbit around the Earth for it to stay there. But the particles of light, the light will take it out of the orbit. So every now and then the satellite has to correct for this. And they have some fuel to correct for this. And it's the lifetime of that fuel is the lifetime of the satellite. So if I send a satellite, I may think it will always stay there, but it is not the case, because you have to always counteract the effect of the uh, momentum of photons and its effect on the solar panels or the entire satellite actually. Okay, so I'll stop here today. So today what we have discussed relativistic dynamics of a free particle. We started with our discussion on the non-relativistic Lagrangian and Hamiltonian, the relation between energy and momentum. Then we wrote down the Lagrangian for a relativistic free particle and found the momentum for that, found the energy for that. We learned three many interesting things: that the momentum does not increase linearly with velocity. We found that a particle can have energy even if it is at rest and there is no force acting on it. And we learned that there can be momentum of a particle of zero mass. Thank you. So that ends our discussion on special relativity.